everyone. I'd like to present molecular dynamics simulations introductory lecture now. And in this lecture, I would like to just talk about how molecular dynamics simulations is useful and what really molecular dynamics simulations are all about. So I've planned the content for this presentation and for the next coming series of lectures of molecular dynamics simulations based on my answers for three different questions. So I'll share those three questions in my presentation now. And throughout the lectures, my main focus would be to answer that three questions. So instead of collecting the information from other sources and putting it as per their structure, I thought I would only cover those few important aspects which are wanted by every one of us from this particular discipline point of view. So let's get started. So the very first question that I'll be liking to discuss now is what is molecular dynamics simulations? So this question uh, will be answered to the considerable level in this very first lecture, but towards the end of the lecture series, I hope you would have a better answer than what I'm giving you now. And the very second question is, why do we need molecular dynamic simulations? So this is rather involved. So I would only try to convince you that molecular dynamic simulations are gaining a lot of popularity for a reason. And I would mention few areas where people are extensively using molecular dynamic simulations and hope that would answer why we need molecular dynamic simulations. And the third question that I'll be focusing on is how do we run molecular dynamic simulations? So I'll just give answer to this in a very abridged form today, but most of my consequent lectures will elaborate on how molecular dynamic simulations are done in the in detail to a lot of other topics. So to start with, what is molecular dynamic simulations? So molecular dynamic simulations is a kind of deterministic tool which is used for analyzing physical movement of particles. So hereafter, when I say particles, I actually refer to atoms and molecules. So we should first notice that molecular dynamics simulations is all about analyzing physical movement of particles. And if you have a question like why should we analyze physical movement of particles, there are many reasons why we should look into the physical movement of particles, but I would like to give you an example of why this is important. So we all know about ideal gas and ideal gas equation. So PV equal to nRT is an ideal gas equation, and there are a lot of assumptions involved in the background for this equation. Although this equation is simple, we can't extend this equation to most of the real gases because the assumptions involved in this ideal gas equation are like these ideal gas particles are particles which have mass but very negligible volume, and all the particles will have equal size, and these particles they don't have the tendency to repel the other particle or get attracted to the other particle, and most importantly these particles they do not experience any loss in energy when they participate in collision. So if collision happens between two particles of ideal gas, that would happen in purely elastic form. So all these assumptions are good when we have systems which are close to ideal, but our real gases are far away from this ideal behavior. So although we know that we can't use this ideal gas equation for real gases, we are kind of limited in our understanding about molecules and their behavior, because of which we have to rely on ideal gas equation. So when we want to really study about the systems which are around us with least amount of assumptions or more realistic assumptions, then we should know the molecular behavior, how the molecule is moving and how it is responding to particles around it. So analyzing particles movement is very important. And way back in 1960s, a scientist called Bernal, along with his assistant Wilkinson, has devised a mechanical model for studying movement of particles in liquids. So Bernal himself has collected hard spheres from bearing, so these are basically bearing balls. So he collected these spheres and he has observed the very motion of these spheres, and he kind of um, made his interpretations as to how molecules of or particles of liquid would flow on a flat surface by looking at the very movement of these particular balls on a flat surface. So his idea was further extended by his assistant called Wilkinson. So I hope you could see these particular images. So this is actually an image of a foam ball used in three dimension.
Actually, Prem, at least
And
I don't think we can see it. The slide is empty. We can see the top header and footer, nothing on the main body.
okay, so I'm now showing these particular images in the slide. I'll quickly reveal all the content of the slide, and maybe then you'll able to see everything clearly. Is the content of the slide now visible?
So, so,
Yes, now
so
now it is.
you see, but
Okay.
if you are on desktop, it's easy to see. So I just changed from desktop, iPad to desktop, and I can see it now. Okay. So others who can't see, maybe they can just refer to the slides which are uploaded on the Files tab in Teams.
Yeah, the file is also available in the Teams files folder.
So if you can't see, you can also look into that and then follow it. Yeah, please go on.
Yeah, so these two scientists have done their work on molecular movements by looking at hard spheres and these spheres which are arranged in three-dimensional pattern. And he insisted that Wilkinson should work on three-dimensional model, and she used foam balls, a kind of a pressure relaxing balls that we use, and these particular balls were held together using spokes. So looking at the motion of these particular balls, she could actually bring out some intuitive observations. And towards the end of these particular observations, they wanted to bring out some output so that they can define the model and the behavior of molecule. But for doing that, they couldn't do it all by themselves. They had to again rely on computers. So I leave it on your judgment whether you call it as a mechanical model or computer model. But the thing is that it is really difficult for us to model the particles just by looking at them. So we have to create some sort of modeling techniques, and molecular modeling techniques is what we really call, or what we usually call, that involve the modeling part of movement of particles like atoms or molecules. So these techniques, they mimic the very behavior of molecules and the molecular systems. And when these particular techniques are used, these techniques require a lot of information related to molecules and their properties. So it is observed that several laws of quantum mechanics are used by molecular modeling techniques in conjunction with classical mechanics. So both quantum mechanics and classical mechanics together, laws from these particular two fields of study were together clubbed and then used for creating modeling techniques. And basically there are two varieties of modeling techniques. One set of modeling techniques we call them as deterministic, and the other one we call them as stochastic. So deterministic modeling techniques are those techniques which take the inputs from us and simply process them and give the output. So if we have n number of parameters in n number of equations, and if we want to solve them simultaneously, we'll provide values for most of these equations and then we'll ask the system to solve it for ourselves. So this deterministic tool just simply solves the equations and then brings out the result for us. Whereas the stochastic methods, they involve some inherent randomness within them because they use random numbers to kind of predict what possible answers are there which satisfies the given problem. So Monte Carlo simulations or these particular stochastic simulations, they don't give you just one answer for a given problem. So they solve the problem in a way that they induce some randomness into the problem solution, and thereby they create all possible set of answers or all possible set of outputs from the given system's problem. So this has got its own advantage in some fields, and deterministic methods have got their own advantage in some other fields. But I just want to highlight that molecular dynamic simulations is one such deterministic tool which is being used extensively nowadays. So just to sum up, molecular dynamic simulations is a deterministic tool, meaning that it doesn't involve any randomness in the very algorithm of solving the equations. And this particular tool is basically used for observing the very physical movement of particles. So how the molecules behave when they are in molecular systems. So I'm going on to the next slide now, slide number 4. And in this slide, I have embedded a video so that I can answer this question like why molecular dynamic simulations are required. Why do we need molecular dynamic simulations? Hope you could all see this particular video now.
Hello.
So basically, yes. And this video clipping is also available in the files folder. So if you have any problem looking at this particular video from the presentation, you can just browse it from the files and access them from there also. So we were in macro scale now. So all the objects in the physical world, they're in the macro scale, meaning that we can actually solve any problem in this particular scale using continuum mechanics. So just to recapitulate what continuum mechanics is all about. So continuum mechanics basically assumes that the material is continuous, which means that whether you take a sample from this particular region or this particular region or any part of the region of your system, you should have sufficiently large number of particles in that particular region. So continuous availability of materials is simply can be understood as continuum behavior. So as long as we stay in this particular macro scale, all the macroscopic methods involve continuum mechanics, and we can solve problems related to macroscopic problems by using continuum mechanics. But as we go into the um, details of this particular object, I'm zooming it into the nib of the pen. And when we see a closer view, we could already observe that this particular surface is no longer smooth. There are a lot of wear and tears, and there are actually a lot of wear marks available or visible in this particular thing, which means that the material which is available on the right side of this particular groove and the left side of this particular groove on either sides of the groove is not available on the groove itself. So there is some discontinuity already observed, and we were now in mesoscale. So our continuum mechanic models cannot actually work here because of the discontinuity in the material. And if we further zoom into the material, if we go into the deeper resolutions, then we can clearly observe the microscopic structures of the surface. And over here, you could notice that there are valleys and peaks on the surface. This surface itself has got different regions. If say this is our system, in this particular region, there is no material available. Because of the peak, the material is available here. So we could clearly sense the failure of continuity principle in this particular region. So if we go little down, we'll reach to nanoscale. So from mesoscale, we'll go to nanoscale. Even in the nanoscale, we'll have particles like atoms or molecules, and we can't really use continuum mechanics principles there, because continuum mechanics principles assume that there are sufficiently large number of particles available in our system, and sufficiently large number sometimes refer to particles count being more than 10 raised to 23. So when we go to this such a small regions or such a small domains, we lack such huge number of particles in our system. So we have very handful of atoms, and if we just zoom a little bit more, we'll get into sub nano level. So sub nano level is where we get the details of molecule or an atom particularly. So when we get into this particular level, we can have a very clear information about the atom, its structuring elements, and different kinds of behavior by the electrons and nucleus and all the other things recorded in quantum mechanic laws. So this is a domain which is well informed about all the principles that happen inside the domain. So I hope you have already observed that we have two domains, the macroscopic domain and this sub-nanoscopic domain, for which the laws are very clear for us. We can actually solve problems based on our understanding that we have for continuum modeling and also for quantum mechanical modelings. But in between, we have mesoscale and nanoscale, for which the continuum mechanics or the quantum mechanic principles cannot be applied. So you could observe the void between these particular two phases, and this void can be filled only if we have information related to the molecular motion or molecular behavior of the atoms or particles. So if we want to really understand what happens in this mesoscale or nanoscale, we'll have to rely on molecular dynamic simulations or any molecular modeling techniques. But why should we really bother about this mesoscale problems or nanoscale problems? The reason that we have to worry about these particular regions is that most of the surface properties can be altered to a very excellent manner if we can operate on the surface texturing or surface properties. So if we can really work on the microscopic elements of this particular material surface, we can bring out a very good amount of change to the behavior of the material on the surface. And you might have also learned that nanotechnology is being rapidly seeing its applications in different fields. And if we want to have a clear understanding about how things work in nanotechnology, we should also have a clear picture on nanoscale modelings. So molecular dynamics kind of bridges the gap between the continuum mechanics and quantum mechanics by allowing us to study the very behavior of molecules. And going to the next question, how do we do molecular dynamic simulations? So molecular dynamic simulations has basically got 5 different steps in it. But before I get into the steps or the parts of molecular dynamic simulations, I want you to observe this very animation which is going on in the right side of this slide. So this animation has all the particles randomly moving in this space. And if you observe carefully, there is one frame in which these particles are positioned in a very organized pattern, and from that frame onwards they tend to move in random directions. So the frame in which the particles are organizedly positioned is my initial frame. This simulation started from that particular frame where all the particles have their organized arrangement within the system. And I have provided the system with the information of all the particles in their respective organized patterns, and I've also imputed random velocities to all these particles in the very first step. And this is called initialization of molecular dynamic simulations. So initialization basically means that we should give inputs related to the particle's position and particle's velocity when we actually start the simulation. And you might have observed that very soon after the initialization is done, in the very next step itself, the particle is no more organized or moving in an organized pattern. All these particles were trying to move in in a very random kind. They don't particularly tend to observe any particular path in their motion. They were randomly moving all around. And you might have also observed that these particles, which are very far from other particles, were moving very slow. And the particles which are trying to approach the other particles, surrounding nearby particles, were trying to move fast. This clearly indicates that all the particles were not under the same force. They have their own force acting on them based on their position with respect to all the other particles. So the next step is to compute the force between the particles. So we'll have to find out what is the exact quantity of force experienced by a particle because of its presence in its neighborhood. So this is the second part. But how do we actually compute the force? How do we know the force which is acting on a specific particle? And that is quite simple, because if a particle is quite close to its next particle, it tend to experience repulsive force, and thereby it is moving away from the closest particle. If the particle is far away from other particles, they were trying to come close to each other, and that kind of hints us that these particles were under weak attractive forces. So based on the separation distance between the particles, we can say whether they are under attractive force or repulsive force, and we can also say what is the exact magnitude of such forces which act between the particles. And all of that information is recorded in this potential function graph. So this is a potential function which is for argon particles, and this is called Lennard-Jones potential. The y-axis here is showing you the potential energy availability because of the particle separation distance, and the very x-axis here is indicating the particle separation distance. If the particles are separated by longer distances, they experience weak attractive forces, if we are very close to each other, they experience strong repulsive forces. And if you want to know what exactly is the quantity of force experienced by a particle if they are separated by 1.35 units of distance, units of r is the distance between the particles. So at this particular quantity, the force is this, and it is falling in the attraction category. So we can clearly understand what is the amount of force experienced by a particle knowing the particle's distance from other particles. But when we compute the force, we should look for the net force on a particle, which means we have to compute force between these two particles, and this particle in conjunction with all the other particles. So we have to compare the force experienced by this particle because of all the other particles, or all the other particles presence influencing the force on this particular particle. So based on that, we'll have to compute the forces for this particle and find the net force acting on a given particle. That is the second step. And in third step, we wanted to basically find out the velocity, the change in velocity with which the particle is now moving afresh in the next time frame. So initially I've given them kind of very uniform velocities in different directions, but you can notice that these particles were at some instance moving faster, and at some other instance they were trying to move slower. And the faster movement is observed when the particle is closely surrounded by other particles. So this particle, when it has more amount of force or acting on it, it tends to accelerate and then move with higher velocities. So from force, I kind of calculate the velocity with which the particle is trying to now move in its new pattern. So new velocities of the particles are computed from force values that we have for a given particle. And once we have the new velocities, I'll try to take the frame and freeze the frame and see where the particle is going because of its new velocity. Say for example, if delta t is a time step, I'll wait for delta t and I'll freeze the frame. I'll see the new position of all the particles. And at this new position of all the particles, I'll try to record the coordinates of all the particles, and that is the next step that I have in the list, which is updating positions of the particles. Once I have the new positions and the new velocities for all the particles, I'll repeat the process once again, and repeating the process over and over again until we reach our simulations requirement is what we consider as the fifth step in molecular dynamics simulations. So this is all about molecular dynamics simulations in short, in brief, but we'll be talking more about this particular simulation and how these particular things are done in detail starting from the next lecture onwards. So moving on to the last slide of my presentation today, I'd like to give you a glimpse of what all to expect from this lecture series. So my major focus would be on molecular dynamics. So I'll first cover algorithm used for molecular dynamic simulations and all the elements which are required for understanding this algorithm. So most of these topics will just go in very great detail. And soon after we complete molecular dynamics part, I would switch to statistical mechanics. I'll just give you some basic introduction about statistical mechanical concepts. And these statistical mechanics concepts will be used, or laws of statistical mechanics will be used extensively for framing our system in molecular dynamic simulations. So I'll also highlight how we can use statistical mechanic concepts for incorporating the system of our requirement in molecular dynamic simulations. I would touch upon the softwares available for taking up different tasks in relation to this molecular dynamic simulations, like ab initio simulations, Monte Carlo simulations, and then VMD, LAMS, all these things. But I'll not be taking you through a detailed version of these particular topics. I'll just highlight them or just mention what really the task of these particular softwares is to in relation to molecular dynamic simulations. So this is all I want to present for today. And before I wrap, I just want to give you an overview of what I have covered today. So we basically tried to answer these questions in today's lecture. So we have seen what molecular dynamics simulations is all about, and we have understood that molecular dynamics is a deterministic tool used for analyzing the very motion of all the particles in a system. So we were intended to study the molecular behavior or the molecular motion in these molecular dynamic simulations. And why MD? The very simple answer, or the very brief answer, would be to bridge the gap between the classical mechanics and quantum mechanics. So we use MD basically to bridge the gap so that we can also explore our studies in mesoscale and nanoscale. And the third question that I have answered is how do we run molecular dynamic simulations, and I'll also be taking this up in the next lectures when I talk about the algorithm used in molecular dynamic simulations in detail. So that's for today. Thank you everyone. Thanks for your patient hearing. And I'd be happy to answer any of your questions. And I'd be more than happy to take suggestions from your end as well. Thank you.
Thank you, Prem, for this enlightening lecture on MD simulations. Is there any volunteers? Are there any volunteers for asking questions? They can. I'll unmute everyone. They can start. Uh, if there are no volunteers, we can just have one question each from everyone. If it's possible, we can start by alphabetically. Okay,
Hello,
Amit has a question.
Amit. Hello, hello. Can you hear me?
Yeah, yes.
Yeah. Can you go to slide number 5? Uh,
Just give me
go
a
slide.
second.
Yes,
This one?
yes. Slide number 5. Uh,
Yeah, I'm on slide 5.
okay, yes. So when you say you update the velocities, update the positions, and then you repeat
Yes.
the steps. So how do we decide like until when we repeat the steps? What is the variable? Like what is the target? For example, if you can explain like what you have decided.
Yeah, that's a very interesting question to answer. So basically, I started with a position of all the particles in an organized way, right? You might have observed that.
Yes,
So in the very first frame, all the particles were in an organized pattern, and all the velocities that I've given to this particular system are from my end. And they don't really have any proper distribution. They were actually random numbers generated using uniform distribution. But in nature, when I sample the molecular systems, I could experimentally find that every particle or all these particular systems will have their particle velocities along Boltzmann distribution. They satisfy Boltzmann distribution. So what I'll do is I'll repeat this simulation for n number of times, and I'll after n time steps I'll check whether the distribution of all these particles is conforming to Maxwell-Boltzmann distribution or not. If it is confirming, I can stop my simulation right over there and I can extract the outputs from my simulation, because my simulation has started from non-realistic phase and evolved itself from non-realistic phase to a realistic phase.
okay. Thanks.
Yeah, thanks for
Hello.
asking this.
Hello, hello. Pinal here.
Yeah, yes, Pinal.
Ah, So I understood that the initially you put the molecule in an organized way, but you have to give them some
Yes.
initial velocity to each and every molecule, right? So if
Yeah.
that initial velocity that affect the number of repetition you have to done, you have to do for a particular simulation, or that velocity won't much affect on the number of steps.
Yeah, if we have a bad choice of initial velocities, obviously we have to run longer to take our system to an equilibrium state. So if we have the sense of what should be the initial velocities, proper initial velocities to reach the simulation end in a faster way, then we have to actually opt for those values. So velocity values, they are really critical to actually decide on how these particular velocities are initially taken. So I have started this simulation with random velocities with one particular value. But if say if my system needs to be at 25 degrees Celsius for about 5 minutes of time, or maybe some nanoseconds of time, then I can take the information from Maxwell-Boltzmann distribution and impute velocities which are close to that particular distribution, so that my system is almost very close to that Maxwell-Boltzmann distribution corresponding to 25 degrees Celsius. So in that case, my velocities are already very close, so I need not wait longer to attain my equilibrium.
So initially you give the same velocity to each and every atoms,
Yeah,
or you have to randomly distribute it.
I have randomly created velocities in between some particular range, and that range
Okay,
is very close to the range of temperatures that I'm expecting for my particles to have at one particular temperature of a given system's
okay,
temperature.
okay,
So,
understood.
and in further lectures, I can also take you through to this ab initio simulations. So these simulations are actually helpful in the initialization step. So you can run ab initio simulations and take the inputs from this particular simulation, the position and velocities from this particular simulation as inputs for your initialization step. This is actually the most beneficial way of doing it, because when we take some arbitrary value, we always tend to go away from this reality. If the system
Yeah.
itself is being started with a value of velocity which is close to the expected system's behavior, then it takes less pain from our end to reach the equilibrium state. Hope this answers your question.
Yes, yes, definitely.
Yeah, thanks, Pinal.
Hi Prem, Raviraj here.
Yeah, hi Raviraj.
My question is that the molecule can go and be in the neighborhood of more than two molecules or three molecules. So are we considering all the forces from all the molecules for a particular molecule?
Yeah, yes. So when I talk about a particle, I compute force experienced by this particle because of the presence of all the other particles in the system. And as you also have noticed, if the particles are quite farther away from each other, the separation distance will be very high, and their potential will be very less, right? So because their potential is very less, the amount of force experienced by a particle due to a particle which is farther away from it is not very considerable in bringing out a appreciable amount of change in its force. So later we develop methods to consider only those particles which try to affect the particle that we are considering in our system. So basically our algorithm is designed for computing force between all the possible pairs of particles. If I take one particle, I'll pair it with all the other possible particles and then I'll compute the force for it to find out the net force.
Okay, thank you.
Okay, thanks Raviraj.
Hello.
Yeah.
Hello. Yeah, Prem. Can you please repeat once that what are the computing force you are taking into account?
Computing force is what I'm doing based on the positions of all the particles. Say this particle is separated by this distance with this particle, and I look at the distance separation between those two particles on this potential function plot. So if the distance is say 1.5 times of r, I'll quickly figure out its force and potential energy, and I'll take negative gradient of this potential energy to find out the force, and I'll say that the force experienced between these two particles is so and so, like x, and I'll compute the distance between other particles with this particular particle, and then I'll compute all the forces. I'll take the resultant of all the forces, and all of this particular force computing process is done in the second step. So it is basically finding out the net force experienced by one particle because of the presence of all the other particles around it using potential function.
Okay, so you are only considering the attractive and repulsive force
Yes, for now only attractive and repulsive forces.
and neglecting other forces.
Uh, like these are, I'm particularly working on argon particles in this simulation, since the other kinds of forces are not really appreciable effects on this particular force between the particles. I'm ignoring them. But say for example, I have a system which involves electrons and ions in the system, then I should also be using some sort of force parameter to account for Coulombic forces also because of the charges. So all those things will come under, will actually modify the potential that I'm using. So then the potential will be looking different than this. So since my system doesn't have any other force in appreciable quantities, or all the other forces were not really significant in my case, I'm just confining to this attractive and repulsive force based on the distance. If other forces are also coming into play, I'll have to change this potential function in such a way that I accommodate all the other effects also into my potential function. And when I talk about the potential functions in one of my next lectures, I'll be discussing what all possible forces are there and what are the possible potential functions we have to accommodate different forces within it.
Okay, thank you.
Hope this answers. Yeah,
Yeah.
thank you.
Guys, we have 10 more minutes. If there are any questions, we can take it.
Hello. Hello, this is Amit. Hello.
Hi, Amit.
Yeah. Uh, how can you say what is the accuracy? What will be the accuracy in this case? As this you have used a 2D diagram. This seems like a 2D diagram.
Yes, yes.
Maybe you have done a 3D, or I don't know.
No, this
So
is basically a very simple simulation. I've done it in only 2D.
yes, sir. So
Yeah,
the results will be very varying when you compare with the 3D diagram. So when you perform a 3D simulations. So what can you tell about that?
yeah,
Because
definitely. So
actually the material will be the motion of the molecules will be in three dimensions. So how accurate is this?
yeah, very true. So I'll talk about this also detailedly in one of the next lectures, but I want you to observe one basic fact here. So these particles, when you see a particle which is coming very close to the boundary, it tends to go out from one particular boundary and coming in from the other boundary. If you observe this particle, this has just gone out and has come in from this side. So this is called periodic boundary condition, and I have applied periodic boundary condition along the other direction. So of course, I've attempted to simulate it only in 2D, but it also has a very slight effect of 3D involved in it because of the nature of boundary condition I've used in here. But you're absolutely true. When I extend this simulation to 3D, I'll get definitely a better result than what I'm doing it here. And to add to that, I can also increase the accuracy or the nature of quality for my simulations when I increase the number of particles inside my system. So all these things are done stage by stage. But as to answer your question, 2D simulations are not really great when compared to 3D, but 3D. But only looking at the cost and other complications into account, we were also doing some basic 2D simulations. But real life simulations are best understood only when we go towards 3D.
Okay, thank you.
Yeah, welcome.
Prem, Anup here.
Yeah, yes, Anam.
Prem, I just wanted to ask, as of now, the system has just argon particles in it. So we
Yeah,
have the kind of potential curve and data for it available for us. So if we go
yes.
for a mixture of gases, so maybe two or three more other particles. So is there
Yeah.
any other source of data that you have for this potential function so that can be used for calculating other forces?
Yeah, based on the combination of particles we have in our system, we have to create that many potential diagrams. Say I have argon interactions in this system. So I have used only argon potential function plot because this potential function graph determines the force when two particles are of argon kind. So say for example I have argon and helium in the same system, I'll have to use one plot potential diagram for argon and argon interactions, one potential diagram or potential function diagram for helium and helium simulations or interactions, and the third one to kind of um, adjust for the interactions between argon and helium. So I'll be requiring three potential functions in that case, or at least three terms in the potential function if I go with two gases, provided all the two gas particles are interacting with each other with particles of their kind with other kind, and also all the three possible interactions are found in this simulation, then we'll have three different potentials. If you have n number of particles available, we have to incorporate a sufficiently large number of potential functions or information from those potential functions so that we'll kind of simulate all the possible interactions between the particles.
Yes, that is what
Does this
I
answer your
wanted to
question?
ask. Just one more extension to it. Like,
Yeah, sure.
are there any other studies saying about the interaction of different interspecies particle, like argon and helium and xenon, other?
Yeah, basically we go with statistical techniques for averaging the interactions between two different species. And moreover, if we want to have real study or most realistic study between interactions of different species, we can again go with ab initio in simulations because that is a groundwork. So we use basically DFT there, and using DFT we can actually extract a lot of information related to the interactions between the particles, and that information can be used in our potential functions. So if we want a very clear information about or very detailed information about all the interactions, we can go with ab initio simulations first, grab our information from there to build our potential, and once we are done with building our potential, we are good to proceed further with our MD simulations.
Okay. Okay. Thanks, Prem.
Well,
Guys, are there any other questions? We have 5 more minutes if there are any other questions. Okay, then if you have any other specific question, you can directly write to Prem or message him. I'm sure he'd be happy to answer your queries. So I would again take this opportunity to thank Prem for this informative session. And our next session of this lecture series would be on Monday, same time. And again, there would be a meeting in the event section. So I'd request you to please join that session 5 minutes before 5 p.m. So, are there any other comments from anyone?
so for now, I'm stopping the recording, and you can
stop the
proceed
recording.
to
Yeah, you
ask.
can stop the recording now.